Hi, I think this is fine now. So can everyone hear me? Yes. So thank you very much for giving me a chance to talk, and thank you very much for coming. I think this is supposed to be a review talk, so I apologize to people who work on the holographic entropy cone, whose work I will not be highlighting primarily, yes, such as Matt, yes. So Matt, I apologize. So a lot of people have done really great work on the holographic entropy cone. A list which is definitely not exhaustive includes Matt Hedrick's group here, and Veronica Hubini's, Sergio Hernandez Cuenca, Ning Bao from Northeastern. So these are, this is definitely not an exhaustive list, but that's a list that includes at least some names that I should mention. Nevertheless, I will be focusing on the work that was done in my group, partly because I know it best. So sorry about that. And that's a lot of people involved. So you see a lot of names here. I hope to be able to talk about maybe not all, but most. I mean, most of the names you see here. Hopefully, I will mention their work in this talk. Hopefully. Okay. So what is the holographic entropy cone? It really is an answer to one of the questions that showed up yesterday in Matt's talk, which is if you have a quantum state, can you represent the entropies in it geometrically? And states for which the answer is no. Dmitry believed that there are no such states, but there really are. So states for which the so states for which the answer is no are the states that we want to exclude from the holographic entropy cone. Okay, and the way this problem has been phrased is as a set of constraints on von Neumann entropies of subsystems. So probably there are constraints that are not write downable in that form. I will probably get to that, in fact, to that question. But one question you can ask is, if all the toys you have are von Neumann entropies of subsystems, then are there combinations of them that are just not geometrizable? And the answer to that is the holographic entropy cone, or whatever it excludes. So the thing that allows us to get started on this is I mean, what do I mean by geometrizable? I mean that there is some kind of minimal prescription, for example, a minimal area prescription, or a minimal cut prescription, or a minimal some kind of local functional prescription that computes entanglement entropies. So Ryu-Takayanagi is the prime example. If you have this goes back to a question that someone asked yesterday in Matt's talk. What if you have, for example, a random tensor network? Well, then the upper bound on entropies given by a cut is actually exponentially close to being the real value of the entropy. So if you in random tensor network states, and so if you ignore those exponential corrections, then there is also a minimal cut prescription there, which is cut the minimal number of bonds with minimal bond dimension to separate a subsystem from its complement through a random tensor network. So that's another place where the same kind of question appears. And just to give you a sense of how this the minimal cut prescription, so equating entropies with minimal cuts, how it gives rise to some constraints. Here's an example, which is really a trivial example of subadditivity. So suppose that I have a system A and a system B, and I compute by the minimal cut prescription its entanglement entropies. So here is some minimal cut, like a Ryu-Takayanagi surface for region A. Here is one for region B. And then, okay, I found them. And now I ask the question, what is the entanglement entropy for the combined region AB? And I have to minimize over all options, yes? But the red surface and the green surface is already one option, right? So I'm looking at, to compute the entropy of AB, I'm looking at the minimum of SA plus SB and other things, yes? So the other things, I drew for you one example of a purple candidate, yes? But you're always minimizing over a set of possibilities which includes SA plus SB. If you minimize that way, you know that the answer is never going to be greater than SA plus SB. You want to make it minimal. SA plus SB is already the worst case scenario, yes? And so right away, we have this relationship, which we know as the subadditivity of entanglement entropy. And this one-liner argument is an illustration of how and why the minimal cut prescription is going to impose some constraints on entanglement entropies. Now, in this case, this argument imposes a constraint which is true in general in quantum mechanics. So we didn't learn anything that was essentially connected to the minimal cut prescription. We just recovered a fact that we already knew from quantum mechanics from before. Subadditivity is a fact that was proven maybe in 1971, directly from the definition of finite entropy in quantum mechanics. However, many other relations also follow from the minimal cut prescription, and unlike subadditivity, they hold not by quantum mechanics alone, but because the minimal cut prescription is assumed. And so they are direct consequences of the minimal cut prescription. And the contrapositive of that statement is that if you take one of those relationships, I will show them to you in a moment, which is derivable from the minimal cut prescription, and you go ahead and violate it, then definitely there was no geometry in which the minimal cut prescription could have produced those entropies. And so in that sense, those things produce for you sort of sufficient condition for an entanglement structure to be classified as non-geometric. Okay. Any other questions? Or not other questions, any questions? Yeah.
Maybe a philosophical tangent. I mean, suppose I ask a different question, which is, I give you a system that has some dynamics and some reasonable large n limit. Some large n system that has some reasonable dynamics. Presumably, depending on how you take the large n limit, there would be some set of restrictions on the entropies of that system, right?
For dynamical reasons.
Well, for dynamicals or just for having a good large n limit, which is well defined. Like, you know, like you have algebras and stuff like that. I mean, there are kind of restrictions that you can have when you go to large n limit. You want a whole bunch of quantities to converge. So that would basically give you some restrictions. And the mean cut procedure is one such restriction, right? It applies in large n theories. So is there any other kind of example? Like essentially, I guess I'm asking about, you know, when you do large n limits, there's this theory of large deviations that tells you that certain objects can be approximated by smooth functionals that you extremize over. So is there something?
I think I'm just going to answer that question with I don't know. Okay, we can talk about it after the talk. I have absolutely nothing useful to say in answer to this question. So sorry.
Can I make one comment that may or may not address it? There are reasons to believe that this entropy cone that Bartek is telling us about is valid beyond holography for other large n systems, which I think is maybe part of your question. Specifically, matrix large n. It's definitely not true for vector large n, so you have to take, it's not just any old large n system, but I think there's a class that goes beyond holography of large n systems that have the same entropy cone.
Okay, so maybe I'm going to actually add something to this, which is that states that do not fall in the holographic entropy cone, they are definitely highly atypical states. And so in some sense I should probably say it already now, which is that the interesting thing about the holographic entropy cone is not what it allows, but what it excludes. It excludes, whatever it excludes, it's states that have some very special structure, and then that structure prevents them from being geometric, but it can turn out to be useful for various purposes. So I don't know if I'll get to talk about that, but I definitely encourage you as you're listening to this to not think so much about what the inequalities allow, but what they disallow. That's where the interesting stuff happens. Okay, and other questions now. So I definitely encourage questions very much. Okay, so here's to give you a sense of what can be derived from the minimal cut prescription. Here is a list of inequalities that has been derived by the same methods, more or less, that was shown on the previous slide. Just a more sophisticated version of the same method, up to August 2023. And what we have here is 9 inequalities. That's the full set that had been known at that time. So at this point in this talk, when I give this talk, I always make this comment, and I hope you agree with me, that this table is both inspiring and disappointing. It's inspiring because you look at this and you say, it kind of is an amazing feat of human reasoning that we have been able to come up with these things. Especially my favorite is inequality number 6. I mean, so Sergio Hernandez Cuenca discovered these, and I just think we owe him a round of applause, even though he's not here, just for coming up with these things. So I mean, I'm gonna do that ceremonially now. And I mean, what in the world could that possibly mean? Yes, and so that's impressive, but it's also disappointing in the sense that it's a little bit like the answer 42 from The Hitchhiker's Guide to the Galaxy. It is an answer, but I mean, what was the question really? The question was about these entropies that are disallowed by the minimal cut prescription, but obviously we're trying to do it to get some insight. And I mean, you stare at this answer just like you stare at 42 and you say, what did I really learn? Yes? And so it's both impressive and disappointing is my comment, and I hope that you agree with this sentiment. Now, I personally felt back in August 2023 that while this table is, well, kind of disappointing because of its sort of wealth of detail, maybe we should make the thing worse. And so, oh no, before that. So this is up to August 2023. And if you felt that this table was kind of crazy back in August 2023, then Ning Bao's group came and made things worse in September 2023, and they gave us 1,865 other inequalities, which look much worse than these ones. And so now we have the zoo of inequalities. This is September 2023. And I personally thought that the matters are not bad enough yet. And so my group and I, in that same month, announced 2 infinite families of inequalities. And so now we have 1,008 plus 1,865 plus 2 times infinity of inequalities. And for these ones, I actually would like to, I apologize for doing this, but I would like you to actually invest 1 minute of your time to understand the notation of this thing, because it's going to be kind of cool further down the line. I promise that this is not time wasted to look at, to try to understand this notation. Generally, when I look at talks, I hate it when people give me a slide with lots of equations and notations and say, well, behold this. But actually here it's useful. And so, if you look at the previous inequalities, they're given, I mean, they contain entropies of various subsystems. And the subsystems here were called A, B, C, D, E, F, G. So here, because of the structure that they have, we need to change the notation ever so slightly and talk about regions that are called A1, A2, A3, A4, B1, B2, B3, B4. They're just arbitrarily named, and they're named into these 2 classes. So let me do this here. So there is A1, A2, A3, up to some A sub m, and there is B1, B2, up to some Bn. And I will always take this index to be cyclically defined. So if you ever see an plus 1, that's the same as A1, okay? And I take this m and n both to be odd. So that's going to be important for us. And now let's, not that I'm assuming this, so I emphasize that I am not assuming any such thing about the actual physical arrangement of these regions in any field theory. However, let's just just for the purposes of illustrating the notation, let's imagine that these regions are arranged like this on a circle. Then A7A. Oh, and it's nice that I ended up with an odd number of regions. And so, so by AIK, I mean a set of k consecutively named regions. And so this collection here would be called A1 free because it collects free regions. Does that make sense? And then the other thing that we want to do is, because I take m and n to be odd, then I want to take, I want to distinguish the largest minority and the smallest majority of regions, which is m plus 1 over 2 or m minus 1 over 2. And so, for example, this region here, the smallest, no, the largest minority out of 9 is 4 regions, m minus 1 over 2. So this here, the green thing would be called a sub 9 minus. It's a 9 because it starts at 9, and it's a minus because it takes 4 things out of 9. Whereas, to give you a different example, this thing, taking 1, 2, 3, 4, 5 regions, the blue thing here would be called A5 plus. It starts at 5, and plus means that I'm taking 5 regions out of 9. Okay, so with that piece of notation, hopefully that wasn't too hard. You look at, we now understand what these inequalities are. And A1M is just the entropy of all the A regions, A1, A2, A3 through AM. Are there any questions about the notation and what this inequality says? So we'll be talking more about this inequality because it has a lot of cool stuff in it. As I will try to convince you, so that's why we're going through this notation. Any questions about that? The algorithm to what? To prove the inequalities? Yeah, I will talk, not to derive them so much, but if you guess them, that I will talk about the algorithm to prove them. But really, they were guessed, so we guessed them. And obviously, we had reasons to guess them, but that's beyond the scope of this talk. Okay, so with the same notation with the upper subscript, we also have this inequality, which obviously looks even more scary. And I call this the projective plane inequality. At this point, this is hard to see why this would be related to the projective plane in any way. But for this one, these are called the toric inequalities, and here it's kind of easy to understand why. Because you see, there is there is a cyclic sum over the index of the A regions, and there's a cyclic sum over the index of the B regions. So in some sense, I am adding up 2 circles, and so in some sense, I'm spanning the structure of a torus. So hopefully that that makes sense why these would be called the toric inequalities. Okay. Any questions about these inequalities? No questions now. Okay, so this is an example of such an inequality, just where you have 5 A regions and 3 B regions. This is what it looks like, and that's like, this is a true fact if you have the minimal cut prescription, which hopefully you will agree with me, that's not something that you would have guessed one morning randomly at breakfast. So the next thing I want to tell you, just to pique your interest, again, this is in the spirit of giving a review talk so that you know what is known, and also my objective here is to get you interested and excited in it, yes? So so by the way, I'm going to be blatantly honest here. If you don't get everything that I say, it's fine by me. All I want you to be is interested in the subject by the time I finish, okay? That's my bar. So I will tell you what, to me, are interesting facts. So the first one is that this inequality naturally lives on a torus. We already saw one reason why that might be true just from the sums, but here is a more complete or more sophisticated version of or like a rendition of that fact, which is that I arranged the terms of this inequality as a tessellation with things that live on the greater than side of the inequality with positive coefficient being faces of a tessellation, and things that live on the smaller than side of the inequality with positive coefficient being vertices of a tessellation. And so when you take these terms and these terms, I'm not putting this term there, this one is not represented in this way geometrically, but if I take these two sums and arrange them on a torus, then they naturally arrange themselves in this fashion. I'm going to tell you about the prescription for how to arrange them here in just a moment, but for now, this is already kind of a nice picture, and you can see that this cyclic structure that is there in the sums is naturally really appears. Now, let's go back to the other scary inequalities, which is these ones, okay? So they definitely look horrendous, but when you arrange them by the same rules as a tessellation, then this is the picture that emerges, and what we basically get is an infinite strip that repeats itself. But when it repeats itself with sort of opposite orientations. So I should say that these inequalities are written in a way that assumes that the full state on all the A regions and all B regions is pure. Because I'm assuming that the state of all of these regions, this does not limit my generality at all. If I have a pure state on m plus n parties, that's the same as having a mixed state on m plus n minus 1 parties. So I haven't lost any generality by doing so. Okay, so with that, but it makes for a much nicer notation. So if I look at, in particular, because I'm assuming that the state is pure, therefore complementary regions have equal entropies. And so let's look at this deep blue square. This is A2, A3, A4, B1. Here, it's A1, B2, B3, B4. These are complementary regions. So even though they look like complements, yes, but they are actually the same entropy as a number. So what you will see is that the terms, the ostensible labels of these regions don't appear, but because complementary regions have equal entropies, therefore the numbers that really they represent do repeat, and they repeat in a way which is inverted on this strip. So here I have blue, green, and whatever color going from bottom to top, but here I have blue, green, and this color going more from top to bottom, yes? And so what I have is a strip which is periodically identified with an additional twist, yes? And so this really is a Mobius strip. Is everyone okay with me claiming that this looks like the Mobius strip? Okay, please interrupt me if the answer is no. Okay, moreover,
Your regions are always double cons, like have topologically trivial, or?
Oh, no, the regions can be whatever they want to be. There's zero restriction on what the regions are in field theory.
Well, then I have a comment. So it's not generically true that the complementary regions have equal entropies. So what is true is that commutant algebras have equal entropies, but then complementary regions doesn't need to be, they don't need to be associated with commutant algebras, and well, we can talk there later, but if it's genetic regions, it's not general, that fact.
Oh, this is like
holography.
It's true in holography.
Okay, so this is like about Hag.
Well, it's true in holography for the leading piece, not for.
So this is like
piece.
Hag duality.
Yeah, exactly.
Okay. Yeah. So yes, definitely. I am ignoring that level of subtleties because the motivation is holographic. But thank you for the comment. Yeah. Okay. Well, the thing is that it doesn't really change anything about the truth value of this inequality, because I can take a copy of the same inequality with the complementary regions, and the statement is still true. So this point here does not affect the validity of the inequality itself, even if we were to incorporate it. Okay. So the other thing I want, but ignoring that subtlety, what happens? So the Mobius. So now we are on a Mobius strip, but the Mobius strip has a single S1 boundary. Yes, like the strip had two boundaries, but after the Mobius strip identification, now I have a single S1 boundary. And what lives on that S1 boundary is terms like this: A1, A2, A3, A4, B1, B2, B3, B4, like all the A's and all the B's. But again, they're complementary to each other. So even though this looks like different squares, they're actually one and the same face. So it is more proper to think about all of these squares that live on the boundary of this Mobius strip as being one single guy, which is topologically a disk. And so this inequality is best thought of as a Mobius strip glued to a disk, also known as the projective plane. And so this is the explanation for why these things would be called projective plane inequalities. Now, remember when I looked at Sergio Cuenca's table from August 2019? Then in it was inequality number 6, and I made fun of it. I said, like, how can you possibly get any structure out of that with these coefficients, 3, 2, something, and something, okay? But on the next slide, I decided to tackle that inequality. And so here it is for our convenience. And I have used the same rules that I used before for the other inequalities. And again, positive terms are faces and negative terms are vertices on a tessellation. And what turns out to be the case is that this fills in a structure like this, which just like the torus could be extended to a plane if I undo the identifications. This thing too has its own like covering space if I continue forever without identifying things. And if I do that, then I will cover the hyperbolic, this tessellation of the hyperbolic plane. If I want to find the fundamental domain here, then this is the fundamental domain drawn for you here. This is the fundamental polygon of the finite, of the compact manifold that we are really doing, that we're really extracting after the quotient, yes. And what this turns out to be is a surface with 4 crosscaps. Every one of these colors, I mean, things being identified by the same color is really a crosscap. And so I end up with a surface with 4 crosscaps, also known as the torus with 2 crosscaps, okay? So that's kind of exciting. So I said, whoa, this inequality, what can it possibly tell me that is conceptual? Well, okay, apparently it knows something about the topology of the torus with 2 crosscaps, yes? And there is, obviously, I hope that you share with me a sense of bewilderment. Like, why is there a structure like that? And I feel that this thing is like homework for all of us physicists to try to understand why, yes? Because things like that, I believe, don't happen by accident, yes? And so it is our job to try to understand why this structure is there. And that's my motivational spiel. Any questions or comments about that? No comments and no questions. Let me just gauge this. There are no questions and comments because you're like so in agreement with me, or because I lost you? Just wait. Okay, thanks. Okay, so far I have I've been a little unfair because I showed you the pictures here, but I haven't explained where the pictures, like how exactly I arrange things. So now I need to talk about the organization of these terms. So I said positive terms are faces, negative terms are vertices, but how do I know which vertex is attached to which face? That's something that I haven't told you yet. And so here's an answer. The answer is that a node, a right-hand side term, will be incident to a face, a left-hand side term, if and only if they do not cross. What does it mean that they do not cross? It's 2 options. Either one is contained inside the other, or they are disjoint. And because I don't care whether I talk about specific regions or their complements, those 2 things are actually the same. Yes, like if they're disjoint, that means that the complement of one contains the other. And so let's just check that this is true. So if I look at this region here, A4, A5, B3, we see that it is contained here, disjoint from this, disjoint from this. Okay, so hopefully you see that this is that I didn't cheat in my picture. And you can say, what is the physical significance of the condition? Why do I care about regions crossing or not crossing? And so let me refer to Matt's talk yesterday. So you can find a bit thread configuration that simultaneously computes the entropies of one region and another region if they do not cross. Whereas if they cross, then you cannot. And so this is a bit thread answer to that question. Maybe a more robust answer to that question is that these are the conditions for entanglement wedge nesting. And that's really a cornerstone of subregion duality. So basically what the not crossing allows us to say is it allows us to forbid the following scenario. Here's one region sitting inside the other, so the regions do not cross. But then their RT surfaces also cannot cross. Here I drew a case where they do cross, and that's forbidden. So entanglement wedge nesting is the statement that this cannot happen, and I get to apply that statement if and only if the two regions do not cross. In other words, if they are neighbors on this lattice. And why can this not happen? It cannot happen because of the minimality of the surfaces that we have assumed. It also, subregion duality really would be nonsensical if it failed, because that would be a statement that the shaded region here can be decoded from X, but cannot be decoded from the larger Y. So by tracing out a piece of Y that is not in X, we would gain knowledge rather than lose knowledge about the bulk. So that's a reason why this cannot happen. Yeah, Jeremy.
So I was wondering if by imposing these extra conditions and the way you glue these faces to each other, are you like trying to like construct or mimic some kind of like version of kinematic space? And like, is this, I mean...
I have an answer to that question on the next slide, or maybe 2 slides from now. Great, excellent. So yeah, so that's exactly the answer to that question. And so what I told you so far is about faces and vertices, but this is not how we do graph theory, yes? So in graphs, we say, here is a set of vertices and a set of edges, yes? And faces are an emergent concept after I embed the graph on a manifold, yes? But here I started from vertices and faces, and edges are derived concepts, yes? So what's an edge? So an edge is, by definition, is something that divides two faces from each other, and it also has 2 endpoints, so it has 2 vertices with each other. So every face is canonically associated with 2 terms here and 2 terms there, on the positive and on the negative side. Let me collect those terms just to get a sense of what is an edge. So for this specific edge, which I highlighted here, I wrote these entropies for you. But then remember that these are entropies of, I am allowing myself to switch the entropy for the entropy of a complementary region. So then if I apply the complementary map on these terms, then I get this expression. And does this expression look familiar to you in any way? This is an expression for a conditional mutual information, which is non-negative by strong subadditivity of entanglement entropy. And so here specifically, this edge is associated with the conditional mutual information of A3 and B1 conditioned on A1, A2, B2. Yeah. And so all edges here are going to be conditional mutual informations. And that gives you a perspective on what this inequality really is. Because suppose that I didn't have this term here, yes? Remember, this is a term which is not represented on the torus, okay? Well, then I would just have these terms which are faces and vertices, but then adding up all of these edges would obviously exhaust them, yes? But then I would say, oh, so therefore this sum minus that sum is just a bunch of conditional mutual informations. In other words, the inequality would just be a bunch of strong subadditivities. So that's a thing that I already know. So the inequality becomes interesting because of this extra term which doesn't live on the torus. Rather than making the trivial statement, a bunch of conditional mutual informations is non-negative, that's just strong subadditivities. Instead, I'm saying, I have a non-trivial right-hand side. I have a non-zero right-hand side. So that's an improvement over strong subadditivity. And notice that this improvement only comes after I have taken those strong subadditivities. Think of these strong subadditivities as, well, here I talked about them as edges, but allow me to talk about them as little pieces of area. This edge is like this piece of area. Does that make sense? So now I'm taking these pieces of area, these strong subadditivities, and I am gluing them together in such a way that I make a compact manifold. And only after I took strong subadditivities and glued them into a compact manifold, I say, oh, now there is a bonus. And that bonus is topological in nature because I have completed a compact manifold out of them. I talked about strong subadditivities being like pieces of area. This can be made precise because the symmetries of conditional mutual information are, the conditional mutual information naturally behaves like a 2-form. So I can always think about it as a little area and just kind of glue it together. And so clearly these inequalities are telling me something about, like, let me restate what they are saying. They're saying, if you have the minimal cut prescription, then strong subadditivities treated as areas glued into a compact surface will give you a bonus. But if you don't have the minimal cut prescription, you don't have the bonus. And strong subadditivity is the best you can do. That's kind of the picture of what we're learning here. Any questions or comments about that? Okay. So so far it has really been the review part of this talk. I told you more or less everything that's known about the holographic entropy cone in the sense of listing the inequalities. There are a lot of other facts known, largely due to Matt and due to other people. I'm sorry that I'm not being exhaustive about the full list of facts that we know about the holographic entropy cone. But in terms of just listing the inequalities, that's everything we know. It's this slide and this slide. That's all we know. And so coming back to the comment that this is both inspiring and disappointing, we clearly would like it to be less disappointing and more inspiring by finding some kind of meaning in those things, yes? So I talked about the toric inequalities to give you a sense that there must be some meaning hidden in them. This structure cannot happen by accident. But it's not an answer to the question, what's the meaning? It just tells you that the hint is even more real, yes, is even stronger with the presence of these manifolds. But we need to interpret this, and the interpretation is the thing that we really are after, and that's the reason why I titled the talk, Applications of the Holographic Entropy Cone. So in the remaining 50 minutes, I'm going to tell you about various things that my group has done in order to interpret those facts. And I will talk about 2, 3, or 4 applications depending on time. I don't care if I don't get through all of them. Anyway, I'll try to give you a list of things that you can, for which these inequalities can be useful outside of themselves. But any questions about what I've said so far? So, while you're contemplating asking or not asking a question, let me just repeat what I said. We just saw messy facts. Those messy facts have some of them have some structure. They're intriguing. Is there an organizing framework? Does it offer new lessons about holography or about large N systems or about something else? And we clearly need some new insight to make progress. And so toward the first application, I'm going to change. This is my way towards the first application of this. We need to, we said it's hard to interpret these facts because there's just too much data. Maybe an artificial intelligence system can just look at this and if it's well trained in human thought, could convert this into some qualitative lesson, yes? But we cannot, just simply because there's too much data in it that we cannot process, yes? So if only we could take this piece of this data that's there and rewrite it in some fashion which is actually like absorbable by the human mind in a glance, then maybe we can get some progress, yes? And so here is a scheme by which we can do that, which is that let me average all those, every inequality by the symmetric group. By averaging, I don't have to keep track of which regions are called A, B, C, D, and E. I just get to talk about how many regions there are in a given term, yes? If I take the entropy of A, B, C, and I average over all permutations, then I will get the average over all free-partite regions, yes? And so that means that I can just replace every inequality, every term in an inequality with the average for the number of regions that it contains. Does that make sense? After I average. So here's an example. Let me take inequality number 5 here, and I'm introducing the notation where S with a superscript is the average of 3-partite, 2-partite, and 4-partite regions, yes? I'm using superscript and subscript because I also need to talk about the permutation group, so otherwise that's the only notation I could think of. Okay, so you get this inequality here out of that one because there are 9 regions on the left which are free-partite, but there's 1 region on the right, so 9 minus 1 is 8, so I have 8 free-partite regions in the end, and then I have 6 2-partite regions, and I have 3 4-partite regions, and so the average of this inequality is this inequality. Okay. Does that make sense what we're doing here? Okay. So with since the procedure is clear, let's just go ahead and apply it to the full table, yes? Like we had we had 9 plus 1,865 plus 2 times infinity of inequalities for each of them. We can just go ahead and do it. And what we find is that there's essentially 1 inequality left. I lied that it's 1 because it has a single parameter. Okay, so there's a single parameter of inequalities for every p where p is p-partite regions. And this looks really nice, yes? So I just want to say, just to check whether you people are have any sense of aesthetics, how many people find this a beautiful result? Please raise your hand. Okay, great. Because if you didn't raise your hands, I would say that you have a heart of stone. So we were really impressed. And actually, by the way, I want to say that these inequalities are, we didn't have to talk about the RT surface. We could just talk about doing minimal cuts on a random tensor network, yes? But then all you have in a random tensor network is just a graph with some weights, and we're talking about minimal weights for a graph, yes? So this statement is essentially it's basically a theorem in graph theory, yes? So you could say, well, graph theorists have been studying graphs for like decades, yes? They should have discovered this. And I searched high and low, I asked my mathematician friends and whatever. No, this had not been known before. And so this is basically a theorem in graph theory. And I am toying with the idea of writing a separate paper about this thing, which is already 2 years old, just for the benefit of mathematicians, because I feel like this should be exported to that world too. But anyway, but that's a fact, yes? So this is like closer to a possibility of interpretation. Here maybe I get to say that there is some interpretation there. So, okay, and by the way, the thing that we saw on the previous slide is an example of that with p equals 3. You can plug it in and you'll see that that's true. So the first thing that you should ask me is, back then, for 3.5 years ago, why would we even, okay, so first we conjectured this. Yeah, you should understand like how it's kind of cute to talk about the progress here. In the beginning, we just had the 8 inequalities from Sergio Hernandez Cuenca, from the table, the 8 inequalities. And based on the 8 inequalities alone, we guessed this thing. So with no further data, just these 8 inequalities, and it's a kind of a lie that there are 8 inequalities. Some of them are related to each other, so there are really 6, yes? Based on these 6 pieces of data, we guessed this inequality. So clearly we had a reason for it. And that reason came from physics. And so I would like to tell you about what they mean physically. That's like our way towards interpreting the inequalities. Yeah, and then we proved it almost 2 years later. And also on a personal note, I want to say that going from the conjecture to the proof is literally the single hardest thing that I have ever done in my life, by far. And I mean, I've crossed glaciers on skis, I've learned fluent Chinese, I've done a lot of things, but this is by far the hardest, okay? So I want you to have an appreciation for like how deep this thing is. Okay, so what does this inequality mean, okay? The thing that we should be thinking about is how do we saturate it, because that's what lives on the border of what the inequality allows, and that's where the interesting stuff happens, yes, where we're marginally away from violating the inequality. And basically, there are 2 ways to saturate the inequality. So the first way is to say that SP is proportional to P, and the other one is if SP is proportional to some quadratic in P, and because complementary regions have equal entropies, at least I'm assuming that, therefore the only quadratic that makes sense is this one, okay, where n is the total number of regions. So the first one I want to say is what's called the perfect tensor-like entanglement. What is a perfect tensor? That also showed up in Matt's talk yesterday. For our purposes, a perfect tensor is something that has 0 mutual information for any pair of regions that don't cover more than half of the system. Once you have more than half of the system, you can't help, for a pure state, you can't help having some mutual information. But if you have one region and another, and they both cover less than half of the full system, then a perfect tensor is a state that has 0 mutual information among them for any such pair, yes? And you can see why that would be true, because if you, so generally our mutual information is the entropy of x plus the entropy of y minus the entropy of xy, yes? So here I called them X and Y because I want to give myself the flexibility of them having different number of parties, yes? Like this X could stand for like ABC or ABD, right? So suppose that this thing has P regions in it, and this thing has Q regions in it, then XY will have P plus Q regions in it. And now what happens when I average? When I average, then this expression becomes SP plus SQ minus SP plus Q. And so if SP is proportional to P, then this will average to 0, yes? Correct? Now, if this averages to 0, that means that literally any pair has 0 mutual information, because subadditivity tells me that this is a non-negative quantity. So if I average a non-negative quantity and I get 0, that means that every term in the average was individually 0. And so this is the statement that nothing has mutual information with anything.
Wait, Bartek, so P is less than half the size of the system? Or?
Yeah. That was in that was here on this.
Oh, I see.
Yeah, that was here. Yeah, that's right. Good. Okay, and so that's the explanation for nothing has mutual information with anything. Now, I want to say that this quadratic also has a structure, okay? And that structure is that it's exactly bipartite or EPR-like. So this one requires some explanation, so let me explain that on the next slide. But are there any questions about what I claimed so far? Okay. So why is this bipartite entanglement? So suppose that you take a tensor network that has only bipartite entanglement. What does it mean that I have only bipartite entanglement? It means that I have dangling nodes on a tensor network. Yes, these are the physical regions. And then I have no interior nodes. That means that every edge in the tensor network directly entangles some degrees of freedom in a system with another system. Now, it doesn't mean that everything is an EPR pair directly, because, well, like let's take this region. It has some entanglement with this region, it has some entanglement with that region. But it's still bipartite because I can think of this structure, yes, this structure, as having arisen initially from having an EPR pair going this way, an EPR pair going this way, and an EPR pair going this way. So it's just a collection of EPR pairs. And after I had this bunch of stuff, then I said, oh, let me forget about the part that these systems are separate. Let me treat them as one system, okay? And here too, let me just treat this as one system. So while your state isn't literally a bunch of EPR pairs, it is related to EPR pairs by local unitaries. And that's what I mean by bipartite entanglement. So suppose that you have a tensor network with this structure. Now, what's a thing that you can say here? So one thing that you can say is that there are, let's suppose that I have n regions in total, yes? Then how many different classes of EPR pair-like constituents can I have here? The answer is that it's n choose 2, yes? There are n choose 2 basic types of EPR pairs that I could construct, yes? So what I want to construct is a quantity called S star, and S star is going to be the total number of lines in this thing divided by n choose 2. That's like, what is this thing computing? This is S star. So what is this S star computing? It's like saying, I have some state which has this structure. I'm gonna take one region, I'm gonna take another region randomly, and I'll say, how many EPR pair-like constituents are there connecting specifically this pair to one another? Does that make sense? So I create this object, and now with that thing defined, I'm going to ask, what is the entropy of any one p-partite region? Well, the entropy of any p-partite region is like, here's a p-partite region, here's it's n minus p-partite complement, yes? I'm just asking how many lines cross from here to there. To answer that question for a specific region, I literally just have to ask to count these lines, yes? But what if is there a question?
So your inequality would be saturated with any numbers as a coefficient, not necessarily 1 to n and p, right? So any m times n minus k times p would have saturated as well for your inequality. This particular thing makes sense about the n minus p side. Was there an explanation for that too?
Yeah, the explanation for it was that we wanted the average entropies for p-partite and n minus p-partite regions to be equal because of that complementarity. And so I said on the previous slide that I can saturate it with any quadratic, but the only quadratic that respects the symmetry between regions and their complements is this one. So that's the reason. Okay, so coming back to here, so if I want to compute the entanglement entropy for a specific p-partite region, then I'm just counting how many lines go from that region to the complement. Now that's a detailed question for which I literally have to do the count. But what if I'm doing this on average? On average, I know that I have p things connecting to n minus p things, and on average, each of them is going to have this many lines running through there. And so the average of the p-partite entropy has to be p times n minus p times s star. And this is the explanation for why that quadratic that we saw on the previous slide captures bipartite entanglement. Any questions about that argument? Okay, and so what we have found is that these what saturates these inequalities is either having no mutual information or EPR pairs, which is like having maximal mutual information. Okay, like I can do better. Yes. Now it makes it sound like the holographic entropy cone is kind of trivial in the sense that the mutual information is either maximal or minimal in some sense, but that's not exactly true. We're going to see that in a moment. But let's exploit these facts and now collect sets of entropes which are extremal with respect to as many inequalities as possible. So these statements here are like what extremizes this inequality for a single value of p. Yes. Now I want to say what are what's called extremal rays of the holographic entropy cone. What is an extremal ray? It's something that that sits in the corner of the cone. That means that it has as many inequalities as possible saturated. Yes. Okay. So when you do that, then you will want to saturate this inequality for every value of p. Is that possible? Well, that's only possible with setting all the entropies to 0. But what the next best thing we can do is to saturate all inequalities except one. Okay, that's the best thing that we can ever do. So what we're going to do is to find the most extreme form of entanglement allowed by these inequalities. Okay, I am repeating what the problem is. I'm going to find the most extreme form of entanglement allowed by these inequalities, and most extreme but non-trivial means setting all of these conditions to be saturated, to be equalities, except for one. Because if I set all of them to 1, then I would just have all entropies equal to 0. So that's the next best thing that I can do in my effort to find something totally extremal. Okay. So that's a set of entropies SP, a set of averages that I have to plot for myself. And when I plot them, I find these plots. And so remember, I'm not saturating one inequality. That one inequality which is not saturated, I'm calling its parameter p prime. And the idea is that I'm saturating the inequalities for p smaller than p prime using the perfect tensor type of stuff. I am saturating the ones past that using the EPR-like stuff. And this is the only thing that can happen. I cannot like saturate with in the EPR way and then go back to the perfect tensor way and then back to the EPR way. So this is the only situation that can happen where I have the red perfect tensor-like saturation on for the smaller values of p and the green EPR-like saturation for the greater values of p. This is the only thing that can happen. And there is that crossover value where the entropies locally are neither perfect tensor-like nor EPR-like, and that's the place where I am not saturating a single inequality. Okay, so these are extreme possibilities. Did everyone understand what I just did here? I tried to describe to you the extreme set of entropies, which are as extreme as possible, subject to these conditions which we have conjectured so far. And they're proven. Any questions about that? So I titled this slide Application 1 with ellipses in order to pique your interest. This is supposed to be good for something. And so what is it good for? The statement is that this quantity P prime, which I have described for you in detail in this fashion, is secretly the age of an evaporating black hole. And that's our application number 1. Okay. So let's talk about that. So again, so what we will find in a moment is that this is what a black hole looks like at page time. This plot of SP as a function of P, where I take every EPR pair, every Hawking particle that's being expelled by the black hole as a separate system, and the black hole itself is another system. So with that setup, the picture that you get precisely at page time is this one. Why is that? Because everything, at page time, every Hawking particle, it's like an EPR pair going back to the black hole. So the whole plot is going to be EPR-like. That's what we have over here, yes? Now, if you extend the black hole evaporation to a sort of logical but ridiculous conclusion, which is that at the very end of the day, the little remnant of a black hole is itself like a Hawking particle, indistinguishable from all the others that left. So that's a sort of logical extrapolation of what happens at realistic times in black hole evaporation. Yes, imagine that I just went all the way to the end, and at the very last bit, my black hole became so small that it's like it itself is like a Hawking particle, which is the last one that left. Okay, well then all of these Hawking particles are related to each other in a maximally random state. And that maximally random state has perfect tensor-like structure, and that's the reason why I have this red stuff. And the curious thing is that if you take a black hole as it evaporates at any intermediate time and compute these SPs, then you get exactly this structure. So let me be more precise about this. So how do we think about black hole evaporation or how have we been taught to think about it in the last, 5 years? We talk about it using the island proposal. So the idea is that there is some reservoir, and that the reservoir is where we have captured the Hawking particles that left the black hole, and they carry little, you can call it wormhole-like structures. I mean, they're geometrizable in the sense that Matt talked about yesterday, yes? And they go into this core, which is the black hole itself. But then I also have an area term, and I'm always competing between the area term versus the radiation term, and I'm checking which one is bigger. Now, so this is accurately represented by this kind of tensor network. So here I drew it as a tensor network, here I drew it as a picture of the island, yes? I have a reservoir, and I have connections going to the interior, and I have the exterior, the exterior of the black hole still within the asymptotic spacetime. And what I'm doing when I compute the entropy of radiation is that I'm having to choose. Either I'm cutting the many legs that are associated with the radiation, or I'm taking the horizon or the near horizon, the quantum extremal surface, to be the place where I do the cut. That's a geometric cut. So I'm having to choose one of those two. When I draw a tensor network which has exactly the same properties, then what I'm really drawing is this, where the mapping is that the black hole island is like the core of this thing. This is the reservoir, and this is the exterior region, which is separated by the area term. Area is like that black thing, yes? What is this? This is a perfect tensor-like tensor network where I have taken some number of constituents and I have just arbitrarily declared them to be one region, okay? So do you agree that what we are taught to think about when we do islands for black hole evaporation is that kind of setup? Just take a random state and many constituents and kind of declare that some number of those constituents are called the black hole, and whatever geometric entropy they have is going to be called the area of the quantum extremal surface around them. That's kind of what we're doing. So you take this stuff with this structure and you compute those average entropies and you get this picture where P prime has to do with there is some formula for P prime which measures the trade-off between how many things you have collected and how many things are uncollected. In other words, the trade-off between the area and the radiation. As the black hole evaporates, the collected regions get smaller because the black hole is getting smaller, whereas the uncollected regions are growing in number because there's more and more radiation. And passing that parameter, or like having that parameter go from the number of these collected regions, having it go from a larger to a smaller value is exactly what changes the shape of this thing and changes the value of P prime. P prime literally is the age of the evaporating black hole. Past page time. Any questions about that? Oh, and by the way, I have a slide here which says that we didn't have to know about islands for this. We could have read Page's paper from 1992 or 1993, and what he's describing there is he's saying if black holes evaporate in a unitary way, then basically I should just be talking about a random state, and some constituents of it are collected together to form the black hole. And what I'm doing is, as the black hole evaporation proceeds, fewer and fewer terms are being grouped into the black hole. More and more terms are exposed in the form of radiation. And so the black hole evaporation is like taking this state, having some set of, this random state, having some set of degrees of freedom collected into a black hole past a piston, and then just kind of pushing the piston so that the part of that's declared to be a black hole is getting smaller and smaller and smaller. So that's what you would get if you read Page in 1992 or 1993, and these tensor networks are describing just that process. Islands are like a more modern version of exactly the same picture. And anyway, saturating these inequalities are the various stages of evaporation of a black hole. And you could say, why did we guess these inequalities? We guessed them from this. We're thinking, whatever it is that saturates there must be some inequalities out there that have that property, that they are extremal with respect to the average. What geometries are there? Yes. Clearly, they have to be some pretty special geometries. It's not going to be like the moon and the earth going around the sun, okay? It has to be something very special. And whenever we talk about special stuff and gravity, the answer is always a black hole. And so we're thinking black holes must be the things that extremize all of these inequalities. So we went from the structure given by Don Page and given by Islands to plus the input from the inequalities we knew to guess this thing. And so I think it's kind of nice that in the end we got a theorem in graph theory by starting to think about black hole evaporation. I mean, if you're not, if you don't think it's exciting, then well, we're not connecting, but I hope you are. Okay. Any questions or comments? I don't know if this was understandable, but again, my goal is kind of to get you excited, so hopefully, or interested, so hopefully I'm achieving at least that goal. Okay, now I think I have time for one more application. I prepared 4 in total, but I don't think that I'll be able to get to number 3 and number 4. So let me talk about number 2, which is, and for that we have to talk about how we prove these things. So again, if I were you, maybe I would be like, oh my God, now I'm going to hear about this like technical proof, okay? But really it's not, there's like a modicum of technicality. The real thing is about what this tells you, and there will be a cool application at the end of it, so please bear with me, and it's really not going to be that bad. So I haven't told you so far about how these inequalities are proven. So here is the most famous inequality of the holographic entropy cone, known as the monogamy of mutual information. And that thing is proven by constructing this table. So these tables generally are called contraction maps, and let me tell you about what they are. So what are the properties of this thing? So the first property is that there are columns here are columns of this table are classified by, are associated with terms on the greater than side and on the less than side of the inequality. And the statement is that if I take the bitwise difference of things in the table has zeros and ones in it, if I take a bitwise difference of terms on the left, on the greater than side of the inequality, then the difference there has to be greater than or equal to the difference on the smaller than side of the inequality. So this is written here in this inequality. So if I compare the first row with the second row, here I have 0, 0, 0 and 0, 0, 1. They're different in 1 bit, yes? What about on the right-hand side of the inequality? 0, 0, 0, 0, 0, 0, 0, 1. They're also different in 1 entry. If they were different in 2 entries, among A, B, C, then this would not be a contraction. Okay, so this is what, this is that condition. That's a condition that we have to satisfy to prove the inequality. And there's one more. The other is that for every region that's featured in the inequality, I call them indicator vectors. Indicators have to map to indicators. So what's an indicator? Let me take the region A here, yes? For every term in the inequality, I'm going to ask you, is A there or is A not there? And if the answer is, I'm there, then you put a 1. And if the answer is A is not there, then you put a 0, okay? So you do it with me just to wake you up a little bit. I'm going to go through these terms and just ask, is A there or is not there? Is A there? 1. Is A there? 0. Is A there? 1. Is A there? 1. Is A there? 0. Is A there? 0. Is A there? 1. Okay, so hopefully that's clear, right? So you go like this through every region that's featured in the inequality, and there is an additional region that purifies everything, which never appears. Like there's A, B, C, and there's a purifier. So for that purifier, the answer is always no, yes? So you also have a row of zeros, yes? Okay, that's also fixed. Okay, and if you find a contraction table which satisfies, if it's a contraction, if it satisfies this condition, and if it successfully goes through this procedure for every region, A, B, C, and so on, then you have proven the inequality. So I'm going to tell you now about why this is a good method of proving the inequalities, and then I will tell you about the cool consequence, which is an application. It's going to be an application to quantum error correction. So please don't be. So yeah, so bear with me if it's getting heavy. So to understand why this is a good proof method, let's prove something simpler, which is strong subadditivity of entanglement inequality. That's definitely a true statement. And so I constructed the table for you with A, B, B, C, B, and A, B, C. It satisfies the conditions that we said on the previous slide. And how do we understand what it's doing? So I first draw the minimal cuts, or the Ryu-Takayanagi surfaces, for all the terms on the greater than side of the inequality. So here's the term for AB, here's the term for BC, yes? And then I mark the regions that are divided in this way with 1s and 0s based on the question, are you inside the entanglement wedge or are you outside the entanglement wedge of that region? If you're inside, that's a 1. If you're outside, that's a 0, yes? Does that make sense? And so, for instance, this region is, why is it entanglement wedge? Well, it's whatever is sitting between the region and the RT surface. I just used the word entanglement wedge for it. So why is this 1, 0? Because it's inside the AB entanglement wedge, but outside the BC entanglement wedge. Why is it 1, 1? Because it's inside both. So hopefully that message is clear, yes? So how do we prove the inequality? The idea is that someone gives us the RT surfaces for the greater than side of the inequality, and we're going to construct some surfaces which satisfy the homology condition, which have already an area which is equal or smaller. But it won't be a minimal surface necessarily. It will just be some surface. But the point is that because we will have constructed some surface which satisfies the homology, some surfaces that satisfy the homology condition, if their area is less than or equal to this, then the true minimum can only have an even smaller area, so the inequality is still true, yes? So if I can find a prescription that always constructs some surface, not necessarily minimal, that is subject, that satisfies the homology conditions for these things, then the inequality will be proven. Is the logic clear? Okay. So So that's the job of the columns on the greater than side of the inequality. And the way this works is that we're going to construct some candidate surface or a candidate entanglement wedge for B and for ABC. So for B, we're going to use this. Why am I using this? I mean, well, because it works, but how does the table know about it? The table knows it for that single one. This one is telling me, take the 1, 1 region, don't take these regions, okay? So I took the 1, 1 region, because there's a 1 here, and I excluded the other regions, because there are zeros here, and that formed my candidate entanglement wedge for B. Does that make sense? Interpreting the next column in the same way, I have 3 1s here, so I'm supposed to take the 0, 1 region, the 1, 0 region, and the 1, 1 region. So that's the yellow thing that I have here, yes? So these are my candidate entanglement wedges that are being constructed by the contraction map. How do I know that the thing that I have constructed has a less than or equal area than the left-hand side did, than the greater than side did? Well, what I can do is, let me look at any piece of Ryu-Takayanagi surface that's there. It's always there separating one of these bit strings from another bit string. For example, this one here separates 0, 0 from 1, 0, yes? And a moment's thought will tell you that counting x minus x prime, how many bits are different in these left-hand side columns, tells me the multiplicity with which the piece of the RT surface, which separates x from x prime, in this case 0, 0 from 1, 0, how many times does it contribute? Here it contributes once, because the thing is different only in the first bit. It's different in the first bit because one side of the surface is outside and the other one is inside the AB entanglement wedge. In other words, this is part of the AB RT surface, yes? And so, adding up this thing computes for me how every piece of area which separates some x from x prime, how many times it contributes to this inequality. What about the candidates that we have constructed? For the candidates, it's the same thing, with the difference being the bits on the right-hand side. So if I have the condition that the x bits and what I call the f of x bits, the left-hand side bits have a greater number of differences among them than the right-hand side bits, then every piece of area individually contributes more on the left than on the right. So the inequality is already true. And then the minimization will further make it even truer, okay? Okay, so that's the reason. And then I haven't talked about this indicator to indicator. The indicator to indicator just ensures that we have satisfied the homology condition. So let me not talk about that, but trust me that that's how this works. Okay, so this is the reason why going through the construction of these tables is useful for, well, it actually achieves the goal of proving the inequalities. And there is a caveat here, which is that it proves them, we are assuming that we're on an equal time slice, or like this time symmetric slice, just like at the beginning of Matt's talk yesterday. So there is a question about what happens to these inequalities when we don't have that. And basically this proof is not valid, and Matt has done very interesting work, and some of it is ongoing, trying to sort of upgrade this to remove that assumption. But here where I'm just assuming that. Okay, so this is the logic of how the proof works. And if you didn't understand what I just said, then it's okay, because you just have to remember one thing. The job of these zeros and ones on the right-hand side of the inequality is to construct a candidate RT surface, or a candidate entanglement wedge for the terms on the right-hand side. That's what we're doing. Okay, so now I am moving towards my second application. And so here is a full contraction table that proves this inequality. These are the greater than side terms, and these are the less than side terms of the inequality. Okay, that's one contraction proof, and you have seen what that does so far. So I want to say that these two entries, circled in red, represent an entanglement wedge nesting violation. What do I mean by that? What I mean by that is that I have a region here which, because of this 0, it is outside the entanglement wedge of CDE, okay? But as I'm constructing my candidate RT surface, I am saying that I want this to be inside the constructed candidate entanglement wedge for CD. How can I be inside CD but outside CDE? That's a contradiction. So let me draw that for you just so you understand what these circles really imply. I have some region which is called CDE, and then I have a smaller region which is CD. Maybe CD is like this. I have some entanglement wedge for CDE, which is given here. And then this specific region that I'm talking about here, it's given by the intersection of the entanglement wedge of DEA and the complement of the entanglement wedge of EAB, okay? It satisfies some conditions. But this 0 specifically tells me that it's outside CDE. So that region is someplace here. This 1 tells me that I want that region to be part of my candidate RT surface for CD. So I'm constructing a candidate, and that candidate has to include something outside. So the picture that I'm getting is something like that. And this region that we have over here represents this region over there, okay? Makes sense or no? That's what these two red circles are telling me. Are there any questions about that? Okay, so you can say, whoa, that's terrible. So this contraction map is wrong because I have violated entanglement wedge nesting. But it's not wrong in any sense because, like I told you, we're not constructing the physical RT surface, we're constructing some candidate surface. And so what we're saying is that this table gave us a prescription to construct some candidate surface. It's just that I already know that this candidate surface will not be the physical one, okay? Okay? Okay. Now, so it's in this sense that contraction tables violate entanglement wedge nesting. In a recent paper that my students and I have written, we have verified that every single one of the inequalities that we know, the 9 plus 1,865 plus 2 times infinity, for each one of them, the contraction tables always have this phenomenon that the contraction map violates entanglement wedge nesting. Moreover, it doesn't violate like occasionally. It violates in a certain in two senses that we can quantify as much as possible. So it really is a rampant feature of these contraction maps that they always violate nesting. Now you can say, oh, maybe I constructed one contraction map and it violates nesting, but there's another one that doesn't. No, but this violation of nesting, at the level of candidate surfaces, not at the level of real surfaces, is a necessary phenomenon. You can see that this is a necessary phenomenon. And by the way, I am building towards an application, so please don't lose interest. I'm going to tell you something about quantum error correction in a moment. So, but how do I know that this thing is really an inalienable feature of all contraction maps? Well, you can see it here by comparing with the boundary condition. Remember, we always have to map indicators to indicators. So this row of the contraction map is something that I'm not allowed to meddle with. That's given by the structure of the inequality itself. That just always has to be there. So my question to you is, what can happen if I go from this row to this row? I'm changing a single bit, which is changing that 1 to a 0, yes? So by the contraction condition, I'm only allowed to change one thing on the right-hand side, yes? So here, I changed this one, which is changed DE, but I left CD unchanged. There was another option, which is to put a 0 here and a 1 here, that would have changed the value of CD, but kept the value of DE the same, yeah? Maybe to satisfy the contraction condition, I could have not changed anything. So I could have had a 1 and 1 on both of them. So basically I have these three options for these two bits. 1, 0, 0, 1, and 1, 1, and 0, 0, sorry. But every single one of them violates nesting. In every case, I would have something which is inside here, but outside there. In the other option, I would have something inside here and outside there. The option 1, 1 is even worse. Then I'm violating nesting in two ways. Like I would have both CD and DE be and contain something which is outside CDE. And so these nesting violations is not something that just happens occasionally, it happens all the time. And what I want to they're inevitable. And what I want to tell you now is that this feature is actually so it looks like one comment you might say is like, oh, okay, that means that these proofs by contraction, constructing these tables, is like a terribly inefficient way of proving things. Because you have to construct something that you anyway know will not physically be realizable. And so like, yeah, okay, it works as a proof, but it has no physics in it, okay? That's like that's an attitude that you can have, yes? So what I want to tell you is that this actually gives us an application of the inequalities, which is that, well, the proof is still valid, and that application is the following. I get to make the following statement. If the inequality is saturated, then every row with a nesting violation, like the previous row, has to be, the corresponding region in the bulk has to be empty. So why is that? So let me make a statement here. For example, here, the statement is that because I have this nesting violation that we discussed right now, then the statement is that if the inequality is true, then a region in the bulk, which is in the entanglement wedge of DEA, but outside EAB, outside ABC, but inside BCD and outside CDE, that combination has to be empty. And why is that true? So the reason why that's true is that the structure of our proof was that we had the left-hand side of the inequality, and what the contraction map guaranteed for us is that I can construct this object which has this feature which violates nesting, which constructs for me some candidate right-hand side, let me call it right-hand side prime, yes? And then I said, oh, minimization, this is still not the physical thing, I get to minimize it. So if I minimize it, then the true right-hand side is even smaller, and therefore the inequality is true, okay? So now, what is this guy here? This thing tells me that the right-hand side prime that I have constructed here is definitely unphysical, yes? If it's definitely unphysical, then it definitely cannot be true that this is equal to that, so I get to put a strict inequality here. And so if this region is there, then the left-hand side is definitely greater than the right-hand side. The contrapositive of that statement is that if the left-hand side is equal to the right-hand side, then this region must not be there. The only way that can happen is that if this region is empty. And so that's the logic that says that this region has to be empty. Okay. So if the inequality is true, then that corresponding region has to be empty. But this is really a statement about quantum error correction, because it's a statement that if we treat the bulk as an error correcting code, then you may give me the following task. You may say, please construct an error correcting code which will act on 6 parties, A, B, C, D, E, and some complement that I will call O. And what I want to have is that I want to have some data encoded in this code so that it's recoverable from DEA, from BCD, but not from EAB, not ABC, and not CDE. This is the bulk codes, the geometric codes that we see in the ADS-CFT correspondence have what's called the complementary recovery feature. Basically, if I take a combination of regions, then any bulk region is either in the entanglement wedge of there or in the entanglement wedge of the complement. Therefore, if something is not recoverable from some combination of parties, then it must be recoverable from the complementary combination of parties. So a more positive way of saying it is that I want a piece of data which will be decodable from DEA, decodable from BCD, and decodable from their complements, which is CDO, DEO, ABO, yes? That's some possible thing that can happen. And the statement is that if this inequality is saturated, then it will not happen. So this gives me a tight, necessary condition for a code to achieve certain error-correcting properties. And that's my second application. And I think I don't have, so this gives me a nice interpretation of the inequalities, because imagine that I started from a situation where the inequality is not saturated, okay? Then I have this region, okay? and then I tune the inequality to saturation, then I know that this region will get smaller and smaller. In other words, my capacity for encoding some data such that it's decodable by those combinations of parties is getting in smaller and smaller and smaller until I reach saturation and it's exactly 0. Okay, then yeah. So in some sense, the inequalities are telling you, pick your favorite combination of parties that should be able to decode your information, construct a code out of them. If this code is geometric in the sense of complementary recovery, then that piece of data that you're trying to encode can never be smaller than 0, okay? And the inequalities are expressing that idea in terms of entropies. Now, let me just tell you that this is not something that happens like occasionally. It happens all the time. So for every one of these inequalities, if you construct the contraction map and you look for instances of these red circles like I have over here for these nesting violations, when I get to make this statement, it's like half the table contains them. So basically, if you take any one inequality of the ones that we know, the 1,865 plus 8, yes? If you take them and if you just ask, like, what is it telling me about, like, which combinations of quantum error correction are made impossible by the saturation of the relevant inequality? Roughly speaking, half of the things become impossible. So so the saturation of any inequality is actually a very strong constraint on what can and cannot be achieved in terms of error correction. Okay, any questions about that? Or about anything? So I think I have 3 minutes until the end. What's the, yeah. So in those 3 minutes, okay. Let me tell you something fun. I don't have time for application 3 and application 4, but I am going to tell you something fun which extends application 2, which is, remember those toric inequalities? And so you might say they are parametric, yes? And so I have an arbitrary parameter. So when I construct the contraction table, it has arbitrarily many rows, yes? Okay, so how do we do it? For smaller values of the parameters, you can like kind of do it by brute force. And here I always make a joke. Please be kind to the speaker and politely laugh when I say that. But when we were working on this, I believe we were the only theoretical physicists who used Microsoft Excel to do our job. So we literally played with this in Excel, which has excellent visualization properties for seeing what the zeros and ones are really doing. And then eventually found a proof. And that proof is the following. So remember, we have zeros and ones for the greater than side, and we have to assign zeros and one for the less than side of the inequality. That means zeros and ones on faces produce some zeros and ones on the vertices. Here's a rule. Every time you have a 0, you put 2 horizontal bars, and every time you put a 1, you put 2 vertical bars on this picture. So you end up drawing a picture like this. And then you decide whether to put a 0 or a 1 on the vertices, which is what constructing a contraction map does, based on the following criterion. If I have a vertex which is surrounded by a trivial loop on the torus, by a contractible loop on the torus, then you put a 1 there. If you have more than one vertex surrounded by such a loop, then you pick one arbitrarily, for example, bottommost and rightmost in this picture. And that prescription, by golly, actually constructs for you a contraction map that proves these inequalities. So you might ask me, how in the world were we able to find this thing? And if you're interested, then I will tell you about this. Obviously, I don't have time to talk about how and why we found this. But this thing has a very interesting consequence. The consequence is that here, if I think about what entanglement wedge nesting, which is the thing that we talked about in application 2, does in this context, it's saying if I ever want to put a 1 here, then nesting says, like, look at it, next to me on the left and on the right are things that contain me, yes? So nesting says that if I have a 1 here, I must have a 1 there. I must have a 1 here. I must have a 0 here, and I must have a 0 here. According to this prescription, what this means is that if I ever put a 1 over here, the only way that this can happen consistent with entanglement wedge nesting is that if it's surrounded by a minimal loop, okay? That's kind of like the rule that I told you before, and it gives you some sense of how and why we found that rule, yes? Like we started to think about ones and zeros by thinking about what is and what is not consistent with entanglement wedge nesting. But remember I said whenever there is a contractible loop, even if it's not minimal, then there is I put a 1 there. This 1 is not allowed, yes, because it has to be a minimal loop if I'm going to be consistent with nesting. So what this is saying to me is that whenever my graph contains a non-minimal loop according to these rules, then I have that nesting violation. Oh, but now I go back to my application 2 and I say, therefore some combination of error correcting decryptions cannot happen. So here's what this looks like. We go back to this inequality and I make the following statement. If this inequality is true, then it is impossible to construct an error correcting code where information is decodable from here, but not decodable from here, 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 and here. These are the things that make this loop, yeah? And I want to ask you, like, I mean, isn't that kind of amazing that the equality of those terms makes it impossible to do that? Here I just drew for you sort of the smallest loop, which is not minimal, where an entanglement wedge nesting violation happens. But let's be bolder and draw this one. I'm going to vanish the previous one. And here is some loop. You can confirm that this is a real loop by drawing all its images. You see it doesn't intersect or anything, so this is a well-defined loop. And this loop is telling me that if this inequality is true, then I cannot construct an error-correcting code where information is decodable from here, not decodable from here, decodable from here, not decodable from here, decodable from here, no, okay, go through the loop and that's that. So this torus knows about these things, and what's amazing is that this is only true for contractible loops, whereas if you make a non-contractible loop, then you don't have a statement. And so the topology of the torus is intimately related to that statement that I said in application 2. So clearly these error correcting codes that we build in geometry have some topological properties that the torus exposed that wouldn't be visible otherwise. And so that's my punchline for now. Thank you.
Questions for Bartek?
Thanks for the nice talk. I wanted to come back to my question about the kinematic space, I guess. So in usual kinematic space, let's for concreteness just take a circle or something, and you consider like all possible subregions on the boundary, and that draws for you some kind of space. So for the circle, it would be like 2-dimensional, I suppose. Of course, this kinematic space is supposed to capture some entanglement properties of the boundary theory, and I think an important statement there is that you need some kind of symplectic structure, and that's sort of intimately related to like strong subadditivity, the fact that you have a bulk description that you can associate to it. I was wondering in this picture where you have like 2 circles with like discretized subregions, yeah, is there some kind of proof of this where you sort of construct a symplectic form and you can derive all these kind of entanglement inequalities, or is that just like too difficult? I don't know. Is there some kind of symplectic structure? Because for now it just seems some kind of space that doesn't have any, any way to.
I mean, my answer to this is that this is a, I made a big deal out of the statement that strong subadditivity behaves like a 2 form. And so that 2 form could be your symplectic form. And so in some sense, this construction of the toric inequalities and the projective plane inequalities is true because I can use conditional mutual informations to sort of design a discretized version of a symplectic form. So I'm completely, so yeah, that's exactly, I think, the right way of thinking about it. And that's, yeah. Mm-hmm. And so indeed, you can think of this torus and the projective plane that I talked about as a new version of, as a new instance of kinematic space, but it's far more interesting than the previous one. And it's far more interesting for the reason that's here on this slide. So in the old version of kinematic space, we had intervals, and there were two parameters, yes? So there was an interval, and it had a right endpoint and a left endpoint, yes? Now, what we have is we have two intervals, the A interval and the B interval, and we're varying we can see it here. So what happens when I go from this phase to this phase? Well, so here I described for you what happens. You add B1, you subtract A3, and you take the complement. The idea of taking the complement was not there in the previous version of kinematic space, and that makes it a lot more interesting. The second thing is that we're talking about two intervals. We're varying one endpoint of one interval, the other endpoint of the other interval, but we're locally not changing the remaining two endpoints of the two intervals. Plus, we're taking the complement. So it's a different operation, which is more sophisticated, and it produces this thing. So I feel like this is like, if previous kinematic space was interesting, then this one is like way more interesting.
Great, thanks.
Thanks for a very nice talk. So coming back to the discussion, which states cannot be represented by geometry, I'm not sure if you talked about this or this is application.
Yeah. So so Matt gave a canonical example of a state that cannot be, and that was the GHZ state on four parties, and the GHZ state on four party has the property, well, any GHZ state has the property that any subset has an equal entropy to any other subset. So if we want to check whether that GHZ state is satisfies the conditions given by the holographic entropy cone, we can just count the number of terms, because every term will contribute an equal amount, yes? And so the first inequality that we have, which is this one, has 3 terms being greater than or equal to 4 terms, yes? In the GHZ state, all of them will be log 2, log 2, log 2, log 2, log 2. So they already know that this is violated. This is not a feature of just this inequality. It's a feature of all of the inequalities. So you can see that here, that I have m times n terms being greater than or equal to m times n plus 1 term, yes? Where is that coming from? If I symmetrize it, then I will get the magic inequalities that I trumpeted in the beginning. And those magic inequalities already have that feature that that the overall coefficient is greater on the right-hand side than on the left-hand side. I mean, 2 over p is actually smaller than 1 over p minus 1 plus 1 over p plus 1. And so so any GHZ state is going to violate these inequalities on 4 or more parties.
Okay, so
and every single one inequality will be violated by it. Yeah.
So of a W state?
Say what?
W state?
The W state, so well, I don't know if that's, I don't know what happens for the W state because I never computed it, but no one told us that it's holographic, so it can go either way, and I just don't know what the answer is. Yeah, I mean, on 3 parties, and there's nothing to, yeah, there is the first inequality is on 4 parties, so so there's nothing to violate. 3 parties. Yeah, thanks. Okay, so I'm a little terrified that there are no further questions, but anyway, I encourage you to talk to me afterwards.
Can you briefly tell us what applications 3 and 4 are?
Oh, great. Okay, thanks. That's the favorite question of any speaker. Okay, so so application 3 is a statement about the. Oh, actually, let me. So application 3 and 4 is about new statements about BTZ black holes. So you can. So I said that the inequalities apply to any setup that you have. So don't take it seriously. But now, for the purposes of this application, I say actually do take it seriously. So take a 2-sided black hole, and when you take a 2-sided black hole, divide one boundary cyclically into regions A1, A2, A3, A4, and the other one into B1, B2, B3, B4. Yes. So, and apply the inequalities there. So, so just for purposes of illustration, I'm going to take this two-sided black hole, this two-sided BTZ black hole, and draw it this way. So here is the horizon, and here is the A regions, and here is the B regions, okay? Does that make sense how I redrew it this way? Okay. So with that setup, I want to say that the region, so this inequality, the toric inequalities that we discussed, yes, they are about terms which have like either just more than half or just less than half of the A boundary and the B boundary, yes? So these things can be in the following phases, okay? And now if I, okay, these are the possible phases for such an interval. And if I go back to the, this statement and I say, how do I go from a neighboring phase, from one phase to a neighboring phase? The way I do it is that I add something on the B side, I subtract something from the A side, and I take the complement, yes? So let's take an example. So it's gonna take like 2 minutes for me to go through this. So, so I think this is okay to talk about. So, if I'm in my two-sided setup, and here is the A region, and here is the B region, and I'm taking approximately half of them, what it means for me to go from one phase to a neighboring phase is to add something here, subtract something here, okay, and then take the complement. The complement doesn't change anything about the entropy. So notice that no matter which phase I'm in, it has to be, it's never true that this point is connected to that point, because that would violate the homology condition for the RT surface. So either they can be connected this way, or they can be connected this way, but there's never a connection that way, okay? So let's just do this one for definiteness. Now I get to make the following statement, which is related to that thing about the two form. Every one of these conditional mutual informations acts like a second partial derivative. There is if you think about this, and you take these two terms and the two terms which are edges and faces, yes, if I put them together, two of them come with a positive sign, two of them come with a negative sign. They really act like a discretization of a second partial derivative of the entanglement entropy of this region with respect to this variation and this variation, yes? So again, let me reiterate the statement. Every edge here acts like a second partial derivative with respect to this endpoint and that endpoint. This also goes to Jeremy's question about kinematic space. So then this second partial derivative is going to be 0, because the entanglement entropy depends on something which is additive between something that depends only on this plus something that only depends on that. There is never, this is why it was important to say that there is never a term that connects them directly, yes? So it looks like every one of these entanglement entropies here is always going to be 0. What's the catch? That can't be true, yes? Because they're greater than the black hole entropy, the term with all the A's and all the B's. So what's the catch? The catch is that here I have assumed that you're always staying in the same phase. So the only way that an edge can have a non-vanishing conditional mutual information is if you're just on the phase transitions. Okay, so now this is a picture of all possible phase transitions that can ever occur between the phases. And remember, when I go from one phase to another phase, I am doing this thing by adding and subtracting regions, and I'm taking the complement. Those two operations are described by red arrows and by blue arrows on this diagram. So when I go from a phase to another phase, what I have to do is take this diagram and go one red arrow and one blue arrow from it. Does that make sense? So for example, from here, I can go to here and then to here, and those two phases could be neighbors, different phases, and therefore they could have a non-vanishing strong subadditivity. So here I mapped for you all possible, this table, I mean this diagram, implicitly classifies for you all possibilities for which edges can be non-vanishing. And now for the final application, let's go back to the torus, where we are on the torus. We had this torus that I have been drawing all along. And then you can ask, what are the faces that are non-zero on the torus? And you get to make a plethora of really interesting statements. For example, there must always be, so first of all, you must always have some region which is in the phase which is at the, well, what are the statements? So one of the statements is that if you ever have these things in these two phases, then those things can only form islands on this picture. Furthermore, if you connect the edges which are non-vanishing, then the following things have to be true. Either you have a phase which goes this way, sorry, a set of edges that are non-vanishing that go this way, or that way, and they're associated to transitions that take me from this phase back to itself. Notice that I can go the red arrow and the blue arrow and go back to myself. That's a phase transition because both this region and the complement are in these smaller phases. So that's a phase transition. If I have edges of this type, then they always have to form these cover non-trivial cycles on the torus, which is either this one or that one. Another possibility that I can have, so these phases always make islands. They never wrap anything. And then the final statement is about this connected phase. This connected phase is if I have sort of edges that are associated with the connected phase, which are non-vanishing, then those things have to wrap either this cycle or that cycle. So this is from the connected phases. This is from the disconnected phases. And the islands are formed by those things that are sort of combinations of, and that are like funny disconnected phases. And so you think about these inequalities, and you think about what happens on the torus, and you get to make these new topological statements. And again, you would never make these statements if you didn't have the inequalities to motivate them. So in that sense, it's an application. So that's one application. And Ricardo, who is here, Ricardo Espindola, is part of the project that's doing this. This is not published yet. And then the other application, I just won't talk about it right now, but ask me offline.
Okay, let's thank Bartek again and go to lunch.
Thank you.